Hello and welcome everyone. So I'll be explaining three problems. The first one is three swimmers. It's from around 742, and in this problem we're given. Okay, let me reload this. Actually, we're given three swimmers and their corresponding time: A minutes, B minutes, and C minutes. What does this A, B, and C minutes mean? They actually refer that if you start at some point, let's say for swimmer 1, if you start at some point after A minutes, you will come back to the point that you started after swimming. That's exactly what it is. I'll show you, and this is okay. I'll show you with an example. Let's say this is swimmer 1. Okay, swimmer 1 starts from here. After a minute, he will come back to here, and after a minute, he will also come back to here. So it is nothing but meaning that a minute is referring that he will go from this his starting position to some ending position, and he will also come back here. So after each a time, he always comes to the starting point. There are three swimmers. For each of them, they've got different minutes of time to go a round out cycle and doing the same thing as the swimmer 1, but in a different time length. Now you were also given P. The P is actually, let's say you are about to watch these three swimmers swim, and you have got your minute P. You will come after P minutes. Now after coming P minutes, the question is that how much time it would take for you to see any of the swimmers come to this point. So let's say you have come to the show after P minutes, and after that, how much time it would take to at least one of the swimmers come to this point. Now, it is meaning that some swimmers, when you come after P minutes, it might possible that some swimmers are already here at the first position. Some swimmers are not already here. Let's say they might be here going this direction. Some swimmers might be here this direction. It doesn't matter. You have to find which one you're gonna see first. Let's say swimmer 1 is in this position, swimmer 2 is in this position, this position, and swimmer 3 is this position. And now at this scenario, who is the first that you might see in the starting position? It always depends on what? The minute, the time minute, the A, B, and C. So for the general observation and the general solution would be that for each of the swimmers, you will find how much time it would take for the person that is that's gonna visualize all these three swimmers, each of them, how much that person is gonna take. It's gonna take time for for each of the three swimmers to come to the starting point. How much time is gonna take for each of the points. So for if I could somehow find out for each of the swimmer how much time it's gonna take after P minutes, how much time it's gonna take for that person to see that swimmer come to the starting position. If I could somehow find out, then I will find out what is the minimum of those time, because the minimum of those time is referring to the first person that's going to come to that point after some minute, which is going to be obviously the minimum out of these three swimmers. So that's it basically. Now how are we going to be dealing with the logical operations? Now the thing is that if P, let's say for some swimmer, ultimately we will just minimize out of those three swimmers. Now for first swimmer, let's say for first swimmer, my P is greater than their A. Now, if that does happen, oh sorry for let's assume that P is less than or equal to A first. Okay, now what is this referring? This is referring that A is already bigger than P, which means P will come less than or equal to. If I say less than, P will come earlier than A. If P is equal to A, then the answer is 0. You will always know. So if P is less than or equal to A, the answer will always be what? A minus P. It will take A minus P for some swimmer to come back to the starting position after the time P. So it would take you A minus P minutes to watch that particular swimmer in that position. So that's the first case if P is less than or equal to A. And what about the second case? And the most important one. What if P is greater than A? If P is greater than A, we have to find out some P which is less than or equal to N times A, or you could say K times A. Now what is this K referring? This K is actually referring that as P is greater than A, it's obvious that I need some times of A to cross over this P. That's obvious. So that's exactly what I have to do. I need some P, sometimes some number of times A to cross P, but actually it's gonna be upper bound of P. Okay, I will try to find out the upper bound of A. Upper bound of K times A will be any upper bound number of P. So that's exactly what we have to do. When we find out that upper bound number, we will just we would know that my new A is definitely greater than or equal to P, and then the rest operation is A minus P. So let me take you to the code section. This is the code section here. Taking the test case, taking the P and the three swimmers values, minute values, and then this is the first case that I talked about. If A is greater than or equal to, or some time minute is greater than or equal to P minute, then the answer for that swimmers will be AI minus P, which means the person that's who's gonna watch this swimmer number A, or any number of swimmer, it's gonna take AI minus P time. And if this case doesn't occur, we'll simply find out the upper bound. This is nothing but the upper bound operation. If it's divisible by that, answer is 0. Obviously answer is 0, because some point it's gonna turn out to the point where P equal to A. So definitely A is gonna be ARRI is gonna be 0. The ultimate time it's gonna take for that person to watch that swimmer, it's gonna take 0 time. And otherwise, just checking the upper bound, you know what it is. Just how this is finding out the K value. Okay, the K value plus 1 is for the upper bound portion. Okay, times ARRI times that minute, as I told you, and then finally doing this operation, which is CC minus P, because this is the upper bound operation which is greater than P. Okay, upper bound operation which is greater than or equal to P. This is for the greater than or equal to, this is for the equal to P, and this is for the greater than P. Okay, so that's it. And finally finding out the minimum out of these three numbers. This is the first that would be the first person that he's gonna, first swimmer that he's gonna visualize by it, and the minimum time would be that. So that's how you're gonna be solving this one. Now let's come to the problem B. Now okay, so for the problem B, okay, so this problem, in this problem you are actually given n cards. it's going to be a permutation. Every card number is going to be pairwise distinct, and in each step now you're going to be going for an operation inside that card deck. How it's going to work? They say that in each step you will pick some integer k which is greater than 0. Take the top k cards from the original deck. Top k cards from the original deck, which means the cards will be distributed like this. If I say 1, 2, 3, 4, 5, let's say, so I can do this operation. This is the top, this is the bottom. So for each k, pick some integer k. I can pick some integer k and take the top k cards from the original deck and place them in order there now. Okay, and place them in order there now, which means I can do this. If I let's say if I pick 5, 4, 3, my new deck operation will look like 5, 4, 3. Okay, and then if I take 2, my new operation would look like 2, and then if I take 1, it will look like 1. Similarly, like this, key cards from original in the order they are now on top of the new. Okay, take the top k cards from the original deck and place them in the order they are now, and on top of the new deck, and then we perform this operation until the original deck is. Okay, so actually they said that if I pick 5, 4, 3, then my new original deck looks like this. If I pick 2, then this 2 will go top of this deck, which means like this. Okay, top of the new deck, it will go like this. Now if I pick 1, it will go here. So as you can see, we are building a new form of deck by allowing this operation to access. And okay, and then they have denoted a function, a logical function, something like they have defined an order of a deck is summation from 1 to n, okay, of which values? N to the power of n minus I times pi. Okay, so if I equal to 1, then n to the power n minus I times pi. Okay, this is the logical operation to find out the order of the deck. Now, what we have to do, given the original deck, output the deck with the maximum possible order you can make using the above operation. Okay, so I have to find the maximum possible operations. So to find out the maximum possible operation, and there is given this logical operation here, it's obvious we need to do some manipulation here to find out and analyze which are the values that profit us the most. Okay, which are the values that gives us access the most and gives us the maximum. If you could analyze it, then if I say that if my pi is the maximum, suppose if my pi, okay, let's analyze it here, n to the power n minus I times pi, right? Let's analyze it. Here you go. Let's say n to the power n minus I times pi. Now this I will be from 1 to n. Okay, from 1 to n I'm gonna do something. Let's say for I equal to 1. Now if you see that, look, just analyze, if I could make this pi maximum possible, what is actually it giving me? And if I could somehow make this pi maximum possible before I becomes much greater, okay, before I becomes much greater, which means I maintaining I as small as possible and maintaining P of I as max as possible, I can get a very, very large value. If you see that, let's say I have found out my PI out of these permutation of 5. Let's say I've got 4, a number 4 at some position from the deck. Let's say 1 3 4 5 2. Let's say now 1 3, let's say 1 3 5 4 2. Okay, now if I see that, what is the maximum from the top of the deck yet? I know that my 5 is the maximum, right? Now when I do that, uh, so for this part, actually what we have to do, just analyze. I need to maintain my I as small as possible, and I need to maintain my P of I as large as possible. If I could somehow do that, let's say for some I, let's say I equal to 1, then what would it become? Let's say n equal to 5. Then 5 minus 1 of 5 to the power 5 minus 1 times 5. Look how big this is. It's really big. If I pick the card in the right position. So what will be the right position? The right position will be that I will pick my card until I reach a point where I get a smaller value rather than a greater value. So I will try to find out a ascending order of cards from the last, and then doing the operation, picking up those cards, putting it in my new card deck. So the only values that matter is PI and I, but I can always maintain my PI because I will always take a cut or a group of numbers where this value will be maximum always. Okay, because each time I'm making a group, I'm making this order of operations. So that's it. Let's take example here. I have taken that. As you can see, if I say this example, I think which example would be the best to suit for? I think the second test case looks solid. Let's take you to the code part. You will understand more. Let me take you to the code part. Where is it? There you go. Okay. Okay. So if you could analyze these examples, what they're actually doing, this example is actually going to give you a tiny bit of hint what you have to do. I remember I said that my PI is the one that matters the most. If I make somehow my PI greater, it's gonna give me the maximum always. So my goal, my ultimate goal is to, let's take 425,361. 4 2 4 2 5 3 6 and 1. So out of these values, remember what I said, I have to pick my card from the top of the deck until some point. Okay, I will pick remember what I told you. I will pick the value that matters the most. I will pick first, my PI need to be greater, so I will always look for the greatest one. Now here in this area, what is the greatest one yet? It's 6, obviously, because in the permutation I know it's as n equal to 6, the permutation would be 6 5 4 3 2 1. Out of this, my target is always start one group of cards where the first position is this, always. So is the position of 6 inside my initial array that is given here. So I will pick this card group first and allow my operation to do. After that, what? After that, I will look for 5. Where is my 5? Here. My 5 is here. Now from this 5, I will pick one group of card from 5 to 3. This will be my other group of card. And I know that after that comes 4. No, after the group of 5 goes, comes 4, group of 4. Now, what are the elements that belong to the group of 4? 4, 2. Okay, 4, 2, and both of them are inside the group of 4. Now, if I then if I then go and try to find out for group of 3, I will notice that it is already been taken by the group of 5. So the general observation is always go and traverse from the descending order, making that value as the group leader, taking that value and the rest of the values, which means the rest of the values which are left, making this as a group leader. That's how we're going to be taking each and every group and then modify those, calculate the values, orders like this. So that's how we're going to be doing. Let's take you to the code part now. Now I'm going to be taking T. This is for the map operations, taking the values and taking the positions of each and every value that is coming. And then remember what I say to you, I will traverse in descending order to make the most out of it. Okay, to make the most profit possible. Then I becomes equal, that's why I becomes equal to n, running this loop until that becomes 1. And this map value is actually checking whether this value has already been taken or not. If it's not taken, then obviously I can make this as a group leader and I can make my operation successful, make an efficient group from that, the one that I told you before. Now I say that yes, this is not used yet. If it's not used yet, make it as usable by tracking it equal to 1, and then from this value I will go from a particular value which is referring which are the values. This LL initially is equal to n because initially every value is available. Now at some point when I take some of those values, I will push it in my until that value LL from the value that I have already taken. Now what I'm gonna do is I will take my efficient maximum values that I've got, and I also know its position, where it's from, till the rest of the values which are left. That is referring to LL. And till that position's value, I will track all of them as equal to 1, because I'm taking all of them in my group to make it maximum possible. And also by traversing in a descending order. That's also notable. And taking that inside my vector. Ultimately, I have to return okay, so I have to actually return the maximum possible order, not the value. Sorry for that. Maximum possible order. So that's easy. Let's just make the groups and make it inside the vector. That's exactly what I did here. Taking the values, just like I said, taking the values and also tracking till what value I have taken and till what values are left. LL equal to TTI minus 1 is actually referring that this is the maximum values inside my group's maximum value, which is the group leader, and that value's position minus 1, because that value's position till the last one already been taken by some groups. So the positions that are left is definitely the positions before the first value that comes, the first descending value that comes to our by traversing the loop. So that's it. After that, we're just returning the vector and making it clearer and all out. Now let's go to the problem C. Now the problem name is maximum width. Problem C, problem name is maximum width. And this problem, okay, you'll be given two integers n and m, and okay, so first let's define what does it mean by the maximum width, or how can we calculate the maximum width. So we can calculate the maximum width. Let's say we're given a sequence till m, and that sequence number are actually values from 1 to n, and okay, let's visualize it first. That sequence number is from okay, 1 to n. Okay, so let's see, let's just visualize everything first. We're given n and m, length of the string, and inside that string I'll be given some of the letters. Also I'll be given a string t, which will consist of m, and it is guaranteed that there is at least one beautiful sequence for the given strings. What is this beautiful sequence? Now they have described that a beautiful sequence is a sequence where the amount of values will be equal to m inside that beautiful sequence. The values, all of them, will be in increasing order inside that beautiful sequence. And also, one condition I have to meet is that my s of p of I equal to t of I. To clarify this, s of p of I, this p of I is referring the index, okay, equal to t of I. Remember, s of something, some index, and t of some index is referring to the characters, strings characters, but this p of I is referring to an index. Now this index, now also one thing to notice is that this t of I consists of m elements, but this s of this t of t string consists of s elements and m elements, and this is s string consists of n elements, and this s string string's index is gonna be denotable. We have to denote it by p of I. So this p of I, and also this p of I consists of m elements. So ultimately, what we have here is, if I say I have a string A, B, 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 C, and M is A, B, C, and I hope that M is less than or equal to N. Yes, absolutely. M also needs to be less than or equal to N. M also needs to be less than or equal to M. So 1, 2, 3, 4, 4, 5, and I have to find out the maximum width. So this is my given string, this is the T string, and what I have to do is, my main task is to work with my T string, which consists of length M. I can make a beautiful sequence by traversing from I can make a beautiful sequence, but that beautiful sequence values will refer to always this T string and each of its character, because that's what they've said. So what I have to do is traverse from the string T. I can let's make a beautiful sequence. How would that look like? Let's say, and they have also said that I will always get at least one beautiful sequence. Let's make one beautiful sequence. Now remember what I said. Beautiful sequence will consist of the values which refer to my string T. So let's traverse from the string T. First character is A. Is there any A available? Yes, there is. So I can say that my index 1 is part of any beautiful sequence. Okay, index 1, because A is here, index 1. And then B comes. Now here B comes. B has index of 2, index of 3, index of 4. It doesn't matter which one you take, but remember, you have to find out the maximum width of your beautiful string. You can make any beautiful string you want, a beautiful sequence you want, but it is mentioned that you have to find out the maximum width. So to find out maximum width, you need to make sure the width inside those two indexes becomes as maximum as possible. So if I get a simple analyzation here, I would be saying that, okay, instead of taking this B, I can take this one, this B, which has the index of 4. That's exactly, and it is also covering this B. So it doesn't matter which B I'm taking, it is covering this B, right? So let's take the 4th index, B. Okay, and then comes what? String C. Is there any string C after that? After that index, actually, after that index. Okay, yes, there is, and it is the only character which is in the string of index 5. Now I can create another beautiful string. How? Like this. One could be 1, 2, and 5. Yes, I can also take that. I can take another beautiful string. How? It could be 1, 3, and 5. Right? So what are the 3 beautiful sequences that I found out from these two strings? One is 135, 125, and 145. Now, how to find out uh, the width, the maximum, how to find out the width out of these, how to find out the maximum out of these 3, maximum width out of these 3 beautiful sequence. If I try to find out the maximum width of this beautiful sequence, it will give me, let's say I have 135, right? I have got 135. So the difference is 2 here, and the difference is also 2 here. Out of the maximum of these two, I've got 2. So the width of this sequence is 2. But if I analyze for either for this sequence or for this sequence, I will get something special, which is, let's see, 145. So for 145, this part becomes 3, this part becomes 1. Out of these two, which is the maximum? 3 is the maximum. So for this sequence, I'm getting an improvement result, which is 3. I'm making improvement of the width of this beautiful sequence that I've also created. And also for this sequence, I will get that 2 minus 1 is 1, okay, but 5 minus 2 is 3. And out of 3 and 1, what is the maximum? 3 is the maximum. As 3 is the maximum, so I can say that the width of this sequence is 3. Now, all possible beautiful sequences are 3, but out of these 3 beautiful sequences, which of those sequences gives me the maximum width? The sequence which has the width of 3, obviously. So that's why the answer will be 3. That's exactly what we have to find out. Now, what is the efficient approach to find out? What could be the efficient approach to find out? If I could analyze this once again, let's think that 2, 3, 4, 5, 6, 7, 8, 9. I'm starting from here. Now I have explained you how the problem actually works. Now let's discuss on the solution part. Remember what I said? I have to make the width maximum, and in order to make the width value maximum, I have to focus on the width of the 2 consecutive indexes. If I could somehow maximize the 2 consecutive indexes of those characters that will meet up, then I can always make it maximum. How is this possible? The thing is, what you will do, the efficient approach is, okay, I've got T string, right? What I will do is, okay, I will match it. First I will match it. I will try to match. Okay, if this character match, always I will do what? I will divide my indexes into 2 parts, left part and right part. What will the leftmost part index will do? The leftmost part and the rightmost part will do the exact same thing, but from a different position. The left part will start from the first position. If I will traverse it, I will traverse it, I will traverse it. If at some point I find some character which becomes equal to the character of my TI, that's it. I will denote it. Yes, this is my member of beautiful sequence, one of my member of beautiful sequence, and I will traverse from left to right, and also I will try to find out the second. I try to match the second character and traversing from the value. So in short, for the left part, what I'm doing is I'm traversing and finding out the first subsequence from string S which matches the whole string T. Okay, so what I have to do is, again I'm saying the left part is doing is that I will try to find out the first subsequence that's gonna give me, which actually is the whole string T. Exactly, that's exactly what I have to find out. And I will denote is, yes, this is one of my possible beautiful sequence. And also I will do the same thing from the right, and I will also match the same string T but in reverse order. Okay, in reverse order, and doing the same thing. We'll do the same thing and make the beautiful sequence. Now what I have actually got, I have got my left string, my left array, which is referring one of the possible beautiful sequence where each and every index is the leftmost index possible from the string S of the whole string T, and doing the same thing from the last and traversing from the last. I'm maintaining the same thing and traversing from the last, but traversing from the last. This portion, or this beautiful sequence will give me the rightmost possible subsequence that I can get, which is actually nothing but the whole string T. Now when I do that, and what I left is two beautiful sequences, which is left and right. But remember, this right sequence initially is reversed, so we have to reverse it once again to make it level up with left string. This right vector or right array will contain values. Yes, it will contain beautiful sequences, but in reverse order. So I have to reverse it once again to make the rightmost subsequence, and the leftmost subsequence is always possible. Now, if I could somehow find out these two arrays, I can definitely maintain my values and maintain the maximum possible width. How? I will traverse. Let's say the total size is length. I'll traverse from not I equal to 0, but I equal to 1 till less than or equal to len minus 1, and I will take my, let's take the code part and see is the pro. Okay, so let's take the code part. You will understand more when I explain you that. Okay, there you go. What we did here is here we did the reverse. Yes, this is the fun part here. I'll traverse it. So I know that my this length is always equal to m, because I'm actually finding out the subsequence that is referring to the whole string t, which means the t's length equal to m. So till 1 till m minus 1, or length minus 1, I have to find out what will be my width. This is my, for I indexes rightmost values that I can get, minus, of course, leftmost values I minus 1. Again, what is this referring? I know that I have to find out width. And what is width? Width is the difference between, width is the maximum out of all the differences between two consecutive indexes. That's what we are doing. But in this scenario, we are not trying to we are trying to make sure the maximum width. That's why one of the subsequences from any position, one of the subsequences will be from the rightmost, and for the same one but for the leftmost sequence, because I have to maintain it from the leftmost. So let's say I have one sequence here I and one sequence here k. I know that I have to make it as max as possible. How am I going to make it? This k, if somehow I can say that this k belongs to the rightmost values, rightmost arrays values, and this I becomes the leftmost arrays values, and they are also consecutive to each other. So if I take one index value from the leftmost array that I have created, the leftmost subsequence created, and if I take the consecutive immediate right values as the rightmost subsequence, this is one of the indexes, that's exactly how am I gonna get. So if I try to make the difference between them, these two indexes, I will get the maximum out of the maximum width. So that's exactly what I did. This is what actually matters. Okay, so the code part is actually easy. Taking n, m, taking the two strings, and this is the vector left and right. This is actually trying to find out the leftmost subsequence which I can get, which is actually nothing but referring to the string t in whole. Also doing the same thing, the rightmost, traversing from the last, finding out the rightmost beautiful sequence. But also one thing to notice, I have to reverse the rightmost beautiful sequence to make it my farthest or my longest, or my, you could say, longest leftmost sequence, you could say. Anyway, we just denoted that rightmost, and then after that, for each of those two consecutive sequences, consecutive indexes, I'm tracking out the maximum width. How? Right I minus left of I minus 1. Of course, it has to be like that. And that's how I'm tracking out the maximum. Yeah. So I hope I made you understand that. And